Welcome back to linear algebra. In this video, I want to talk about the idea of isomorphism, which might be the single most important idea in all of linear algebra. Now that we've spent several videos talking about vectors in general and how we can talk about all these things that are not Euclidean vectors and pretend that they're vectors anyway, we have this amazing result. Let V be any n-dimensional vector space. Right? So the polynomials of degree n minus 1. If n is not a prime number, the p by q matrices where p times q is n, or anything else. With just that information, there is a rule which is known as an isomorphism, which allows any vector in this vector space V to be represented as a Euclidean vector in Rn. And I do want to stress here, this is not an accident. When we have an n-dimensional vector space, we're going to work in Rn. There is, to put it in other words, there is a sense in which every n-dimensional vector space is actually the Euclidean vector space Rn, just written in a somewhat strange manner. If that doesn't seem mind-blowing to you, then you're probably in the wrong course. The first time that I saw this, I just had to stop and blink a couple of times and say, wait a second, that doesn't make any sense at all. We unfortunately don't quite have enough information here to prove this claim today in this video. In the next couple of videos, I'm going to show you some of the theory behind why this works. But this is such a big result and it's so useful that I think that it's worth putting that result first and then looking into how we know that it's true a little bit later. So how we know that this is true? Well, first of all, the idea of an isomorphism is actually a little bit more general than this. The true meaning of an isomorphism is that an vector in any n-dimensional vector space can be represented as a vector in any other n-dimensional vector space. It's just that the Euclidean vectors are the useful ones. It is so much easier to work with Euclidean vectors than with any other vector. So if we can get it to the Euclidean vectors, that's usually the rule of thumb. That's usually the thing we care about. For practical applications, the purpose here is going to be into numerical analysis and computer science. There are a ton of numerical computation libraries available for various different programming languages. If you are dealing with linear transformations on Euclidean vectors, there is software available that has optimized the computation no matter how big the vectors happen to be. You have 500-dimensional vector space, that's fine. The computer can handle it. And so we take whatever kind of vector we have, we rewrite it as Euclidean vectors, we rewrite our transformations as transformations on Euclidean vectors, and then we tell the computer to do all the work. So even though isomorphism is general, Isomorphism relates any two vector spaces of the same dimension. It's the Euclidean vector space that is actually useful to us, so we're going to pretend that that's the only one that exists. All right, all the caveats out of the way, let's actually do one of these things. So recall that a transformation T is a function which maps from one vector space, called the domain, V is how we're going to call it, to another vector space, which we call the codomain, W. Recall also from calculus or from somewhere else that a function has an inverse if and only if it is both one-to-one and onto. You've probably spent more time around the one-to-one definition than you have the onto definition, but they are both important. One-to-one, you learn about when you deal with functions of one real variable. The squaring function fails the horizontal line test, so it is not one-to-one. The cubing function satisfies the horizontal line test. There is no horizontal line that passes through the cubing function more than once, so the cubing function is a one-to-one function. When you're talking about real valued functions of one real variable, like you do in your college algebra and high school algebra classes and even into calculus, that's really all you need in order to have an inverse. The idea of onto is a little bit trickier. The idea of onto has to do with how much of the codomain and range matter. And that's something that we're going to talk about in detail in the next couple of lessons. But up here in my definition of the transformation, I mentioned the second vector space W. I called it the codomain, which is something that is subtly different from the range. We talked about that a little bit when we talked about linear transformations on Euclidean vectors. The range is the set of vectors that you actually get to, which is a subspace, a subset, which is a vector space, so a subspace of the codomain. For a function to be onto, the range and the codomain are actually the same vector space. We're going to analyze that idea in detail in the next several lessons. I'm going to give you a sneak preview of the conclusion that comes out of this. A linear transformation T is both one-to-one and onto only when the dimension of its domain is equal to the dimension of its codomain. And so For any invertible linear transformation T going from some vector space V to some Euclidean vector space Rn, it must be the case that the dimension of V is n. Again, if you think about this geometrically, it tends to make sense as well. The dimension of a vector space talks about what the geometry of the vector space looks like. A one-dimensional vector space is a line. A two-dimensional vector space is a plane. A three-dimensional vector space is the space we live in. So if you have a three-dimensional vector space, that is something that looks like real space, and you have a quadratic polynomial, which is a three-dimensional polynomial, I guess, the representation has to be the same. The space that you are working in has to be the space that you deal with. And so that's not proof, but again, we'll talk about that in the future. We're going to build up the theory and show why this has to be the case. But for right now, I'm just giving it to you as given to help justify that a linear transformation T from V, I should build up a little bit more of this theory. Let V be an n-dimensional vector space. Let S having components, let's go with B. Let B having components, B1, B2, down through to Bn, be a basis for V. And define a transformation T from V to Rn by T acting on A1, B1 plus A2, B2 plus all the way down to AN, BN is going to become the column vector A1, A2, all the way down to AN. I claim, first of all, that T is a linear transformation. And second of all, that T has an inverse. And it seems like so little for the big deal I've made out of this, but those two facts together are exactly what it takes to say that something is an isomorphism. Again, an isomorphism like this is the one that's useful, but it's certainly not the only way we can talk about an isomorphism. All right, so let's see. I claim that T is linear. So let's take two vectors out of V. And so we can name them. V is going to be A1B1 plus A2B2 plus all the way down to ANBN. And W, I guess, is going to be C1B1 plus C2B2 plus all the way down to CNBN. And if I take my transformation on PV plus QW, we can do a whole bunch of messy algebra. I don't want to have to write it all out, but I guess I can. We're going to have P times A1 times B1 plus Q times C1 times B1. We're going to have P times A2 times B2. We're going to have Q times C2 times B2. We're going to have P times AN times BN. We're going to have Q times CN times BN. And the thing that really matters in all of this is that we're taking the transformation of PA1 plus QC1 all times basis vector B1. We're taking the transformation on PA2 plus QC2 times basis vector B2, and we're continuing that all the way down to PAN plus QCN all times BN. And given the way that the transformation is defined, that is important because now I can write my transformation as the column vector, which is going to have components PA1 plus QC1, PA2 plus QC2, all the way down to PAN plus QCN. Now that I'm in the Euclidean vectors, I can split this up. I can write it as P times A1, A2, all the way down to AN, plus Q times B1, B2, not B, C. C1, C2, all the way down to Cn. And I can remind you that this is exactly P times the transformation on V plus Q times the transformation on W. So that's what it takes to show that this transformation is in fact a linear transformation. To show that a transformation has an inverse, sometimes it's worth just trying to work backwards. All right, so for part 2, again, remember we want to show that T has an inverse. An inverse would be another function, T inverse, which is going to go from Rn to V. So pick a vector u in Rn. And from the definition of a vector in Rn, this is going to be some A1, A2, down through to AN. Right. All we've done is said that we have a random vector in Rn. And from just that, we can use the components of vector u as coefficients and write a linear combination of basis vectors. And because a vector space is closed under linear combinations, this must be in our vector space. Let's call this thing little v. And the transformation of little v is in fact equal to u. So we know that this function has an inverse. If we are given a vector in the codomain, we can find a vector in the domain that matches up every time. So we have an onto function. To show that it's one-to-one, we should also show that this is going to be unique, but that's a little bit beyond what I honestly care about right now. What I really care about is that this structure is one we can work with. Sometimes you will see this called the canonical isomorphism for basis B, or sometimes you will see this called the basis representation isomorphism. And the reason I care about this is it's exactly what we were doing in the previous video. If we have a set of basis vectors, right? If we have S is equal to U1, U2, down through to UN, and we figure out that our vector V can be written as C1U1 plus C2U2 plus all the way down to CNUN, and I represent V under S as the ordered n tuple, C1, C2, down through to Cn. Well, if I just take that and write it as a column vector, I have a vector in Rn. Right? That transformation is the isomorphism. And so this tool is the tool that I use in order to write things as those n tuples and do work on them anyway. I really have column vectors. It really is a vector in Rn. And the power of an isomorphism is that once you do this, any work that you do will translate. For right now, the only work we have that we can do is linear combinations, which we know always translate. But sometimes that's a little bit hard to see in odd representations of a vector space. So for example, we know that S 1 plus x, 1 minus x is a basis for P1. In the previous video, I asked you to show how you can take any linear polynomial and write it under the basis 1 plus x, 1 minus x. Now that we have the language of isomorphism, I would like you to actually write those instead as column vector representations of the, column representations of these vectors under this basis. I'd like you to do that with the vector 3x plus 5. I'd like you to do that with the vector 2x plus 3. And then I'd like you to see what you get when you add those two vectors together under the representation, turn it back into polynomials, and verify that everything worked out for you. All right, take a couple of minutes to play around with that, see what you come up with, and I'll see you in the next video.